In this lecture here, we want to start talking in more detail about functions and their graphs. So in the previous lecture, what we did was we introduced kind of like the basic concepts of what a function is and what its graph looks like. So in this lecture here, now we want to dive in a lot deeper. Okay, so what we're going to work through here is we're going to first start talking about intervals on which a function is increasing, decreasing, or is a constant function. We're going to use the graph of a function to locate what we call relative maxima or relative minima. We're going to identify even or odd functions and recognize their symmetries. And then what we're going to do is we're going to talk about piecewise defined functions. And I'm going to talk about how you graph piecewise defined functions. And then the last thing we're going to do is we're going to simplify a function's difference quotient. And the difference quotient is going to be really important because if eventually you want to go into study of calculus, you're going to see this difference quotient a lot in the future. So we'll introduce it here. It might come up again if you take pre-calculus, but then once you get to calculus, this difference quotient is going to be a major part of the course. All right, so let's start with intervals of increasing or decreasing. And these definitions here are very, very wordy. So what I'm going to try to do is I'm going to give you the definition and then explain it a little bit easier. So a function is increasing on some open interval I, so some interval I, if f of x1 is less than f of x2 whenever x1 is less than x2. And this is for any x1 and x2 in the interval. Okay, so what does this mean? So a graph is increasing. Let me show you. So suppose you have a graph and it looks like this, okay? Okay, just like this. If you pick any x1 and x2, what you're going to see is that f of x1 is less than f of x2, all right, as you move left to right, okay? So as you move left to right, so as I go from x1 to x2, the graph goes up. So just think of that. As you go left to right, the graph goes up. All right, so it's going up. So as I go, think about it, the way, I know this seems silly, but imagine as you're like walking across the graph, okay, you're a person and you're walking across this graph. As you go left to right, you're walking upwards. So now decreasing is the flip. So a function is decreasing on an open interval I if f of x1 is greater than f of x2 whenever x1 is less than x2. This is for any xi in the interval. So let me show you this. So decreasing would be something like this. x1 is less than x2, but f of x1 is greater than f of x2. Okay, so what this means is basically, sticking with my analogy, as you're walking along the graph, as you go left to right, you go down. So as you go left to right, the graph goes down. All right. So a constant function, so a function is constant on an open interval if f of x1 is equal to f of x2 for any x1 and x2 in the interval. So what a constant function is going to look like is it's a horizontal line, basically. All right, so whatever x1 and x2, they're the same f of x value. Okay. So what I want to do next is I want to do some examples. I'm going to throw up some graphs, and I want to say, okay, what intervals is the graph increasing? What intervals is decreasing? And if there's any intervals where it's constant. And the important thing here to note is that when we go to find these intervals, we're going to write them in interval notation, and they have to be open intervals. So they're going to get open brackets. So that'll make sense when I start explaining this. Okay, so let's look at this one. So I've got this y is equal to x squared. So here's the function, basically. I've got y is equal to a function of x. It's x squared. Okay, it's a parabola. And I want to state where the intervals where the function is increasing or decreasing. And it's such a common mistake to say, look, the function's going up, it's increasing everywhere. But that's not true. So look, think of it as a person walking on the graph. As I go left to right, what's happening here? I'm going down. I'm going down. So as I go left to right until I get to 0, so for all negative numbers, until I get to 0, I'm going down. So it's decreasing. So it looks like it's decreasing from negative infinity to 0. Okay? And then look, once you get past 0, as you go left to right, the graph is increasing. So it's increasing from 0 to infinity. Okay, we'll talk about what happens exactly at 0. Okay, that's going to be a turning point. That's going to be what we call extrema. But for now, just remember, as you want to find these intervals of increasing or decreasing, think left to right, left to right. So as I go left, I'm walking down, and then once I get to 0, so I'm decreasing here, and then once I get to 0, I start increasing. Okay. Let's do another one here. So I've got this graph here. So state the intervals on which this given function here is increasing or decreasing. So look, you're going to go left to right. Okay, so I want to find where it's increasing and where it's decreasing. Well, look, so starting at negative infinity all the way to the left on this x-axis. As I go left to right, I'm going up. Up, 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 until I hit here. This x value is negative 1. So it looks like I'm increasing from negative infinity to negative 1. And then from negative 1, I'm walking down, 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 until I get to x is equal to 1. So it looks like I'm decreasing from negative 1 to 1. And then once I get to x is equal to 1, I start going up again. So I'm going to union it. It's going to be from 1 to infinity, I'm increasing because this x is going up, 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 up as x increases without bound. So just, again, always work left to right, left to right. All right, let's try this one again. All right, so just another one so we can make sure. So I want to find the intervals it's increasing or decreasing. All right, so left to right. So this has these arrows imply it goes on forever here. Starting at negative infinity along the x-axis, it looks like I'm going down, 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 down. I'm walking down, down, down. The function's going down until I hit negative 3. So it looks like it's decreasing from negative infinity to negative 3. And then look, once I hit negative 3, I'm going to start going up on the graph. I go up, 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 up until I reach this point. So that's the x value, negative 3 to 0. So I'm increasing from negative 3 to 0. And then after x is equal to 0, I start walking on the graph and I'm going down. So then it's decreasing from 0 to positive infinity because this graph is going to keep going down, down, down into the right forever. So I hope this analogy makes sense. I know it seems silly, but like just think of you're walking on the graph left to right, left to right. See where you're walking down and then see where you're walking up. Okay, now I want to talk about relative maxima and relative minima. This is also what's referred to as relative extrema. This is these concepts here you'll revisit when you get to calculus and pre-calculus and then calculus. So a function value f of a is a relative max of f. Okay. If there exists an open interval containing a such that f of a is greater than f of x for all x not equal to a in the open interval. Okay, what does that even mean? Okay, so what this means is when you look at the graph, you have a relative max at any peaks. Okay, any peaks in the graph. So what I mean by a peak going back is something like this. This is like a peak. This is a peak of the graph, okay? Think about it like the top of the mountain. I'm at the top of the mountain. So that's a relative max value here, this top of the mountain here. A function value f of b is a relative minimum of f if there exists any open interval containing b such that f of b is less than f of x. Okay, this is for all x not equal to b in the open interval. So what does that mean? Well, that means this concept of a relative min, all right, at any valleys. Okay, so think about peaks and valleys. So if you look here, if you're walking, it's like I'm walking down, 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 and this is the valley. This bottom part is the valley. So this is what we call a relative min. So it's a relative min because relative to values that are close around it, it's the minimum. Okay, it's not obviously the minimum value of this graph, right? Because even over here is a lower y value. But it's a valley. So relative to the values around it, it's the minimum. And the same deal here. This peak, this top of the mountain, is a relative max relative to the values around it. Because you look over here, this value is higher, and so on. So what I want to do now is I want to look at graphs and show you there what I mean by the relative max, relative min. So this one here. So let's identify the relative maxima and minima of the graphs of this function f. Okay, so I've got this function f here. So relative max occurs at peaks. So this value here is the max value, relative max value. So we say here f has a relative max at x is equal to -1 because that's the peak right here. And the relative max value would be f of -1. Okay, so whatever this is here, we don't see it perfectly on there. Okay, but that would be the relative max value. And the relative min occurs at the valley. So the peak of the mountain, oh, I walked down and I'm in a valley here. So this is the relative min. So f has a relative minimum value at x is equal to 1. And so we'd say that relative min value is f of 1. Okay, so when you're looking for relative extrema, either relative max, you look for the peaks. Relative min, you look for the valleys. All right, let's try this one here. Okay, so going back to this graph. Let's identify the relative maxima and relative minima of the graph. All right, so let's do relative max first. So the relative max, if you look here, look, here's the peak. This is the relative max. So the relative max, it occurs at x is equal to, and what's the x value here? X is equal to 0. So the relative max value is f of 0. Well, f of 0 here is the value 3. Okay, so we have a relative max value of 3, which occurs at x is equal to 0. Let's talk about relative min here. So where's there a valley? Look, it's right here. Okay, so this is the relative min. So we have a relative min that occurs at the x value, so x is equal to -3. And the value, the relative min value, is f of -3. So f of -3 is the value actually -3. It just worked out that way. All right, so this is important. The relative max and relative min occur at the x value, but their value is the function value evaluated at that, okay, at that x value. Now, not every graph has to have both, okay? It doesn't even have to have either. Like if it's a linear function, it actually has neither. But like for example, let me just go back and let me show you one that has neither, okay, just real quick. If you just consider, actually I'll go back to this on here. Sorry about this. If you consider this one here, do you notice how this graph x squared only has a valley? Okay, so this has a relative min at x is equal to 0, which is the value f of 0, which is 0. But do you notice how it has no peak? All right, it has no relative max. All right, because it has no peak. So it's okay. It's okay to have one or none. Okay, you can also have multiple relative max and relative mins. It just depends on the graph. Okay, there doesn't have to just be one of each either. Okay, let's take a look at this one here. All right, and so this is like a complete example. Okay, let's identify, looking at this, relative maximum minimum of this graph, and then finally let's state the intervals on which the given function here is increasing, decreasing, or constant. Okay, so let's start with relative max. Okay, does it have any peaks? Absolutely it does. It has a relative max value of 16. So the relative max value is this y value, this f of x value, which occurs when x is equal to -2, right there. Has a relative min. Okay, so look, do you see anywhere where it has a valley? Yes, absolutely. It has a relative min value of -16, which occurs, it looks like it occurs at the x value 2. Okay, so you want to state what the value is and look where it occurs. Now let's do intervals increasing or intervals decreasing. So look, as you go left to right, if you start at -infinity, you're going to be going up, 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 until x is -2. So it's increasing from -infinity to -2. And then once you get to x value of -2, you're going down, 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 down until x is equal to 2. So it's decreasing from -2 to 2. And then what happens after you get to x is equal to 2? You start walking, going upward again. So then it's increasing from 2, and then you'd keep going to infinity. So you can tell a lot just by looking at the graph, right? You can see where the relative max, you can see where the relative min is, and then you can also observe and look at where the function's increasing. So as you go left to right, that it's going up, or it's decreasing. So as you go left to right, it's going down. Okay. Next, I want to talk about even and odd functions, okay? So we classify functions, they can be, let's call it an even function, an odd function, or a neither function. Actually, it doesn't have to be, things aren't just even or odd, they can be neither. All right, so a function f is an even function. If you take f of -x, you get the same thing as f of x, and this is for all x in the domain of x. Okay, so what happens here is the right side of the equation of an even function does not change if x is replaced with -x, okay? And so the graph of an even function is symmetric with respect to the y-axis. So what that means is, like, if you were to cut the graph in half on the y-axis and fold the y-axis over, fold the two sides over onto each other, they'd be mirror images of each other. They'd fall perfectly. So a function f is an odd function if f of -x ends up being equal to -f of x, so negative of the original function. Don't worry, I'll show you an example of all this, okay? And this is for all x in the domain of f. So what this means is every term on the right side of the equation of an odd function changes its sign if x is replaced with -x, okay? So the graph of an odd function is symmetric to the origin. So what that means is it looks the same upside down or right side up, or the graph is the same when it's reflected across both the x and y axis. And so I want to show you now how you can identify if functions are even or odd. Okay, so even if f of x is equal to, or f of -x is equal to f of x, and it's odd if f of -x is equal to -f of x. And it's neither odd or even if neither one of these things hold. Okay, so let me show you an example of an even function. Okay, and I'll prove it to you. So if you take f of x is equal to x squared plus 6. If you look at f of -x, okay, so this becomes -x squared plus 6. Do you notice when you square the negative, you just get back to x squared plus 6? So it's even because f of x is equal to f of -x. So we know that's an even function. All right, so this one's going to be an odd function. All right, if you look at f of x is equal to x cubed minus 8x. All right, let's see what f of negative x is equal to. So I'm going to plug negative x in instead of x. Well, negative cubed here, so negative x cubed ends up getting you just minus x cubed. And negative negative is positive, so this becomes plus 8x. Well, let me factor out a negative. When I factor out a negative, look what I get. I get negative and then x cubed minus 8x. Well, look, x cubed minus 8x is just f of x. So look what's happening here. I'm showing that f of negative x is the same thing as negative f of x. So that means it's odd. Suppose I don't tell you, okay, and I just say determine if the function is odd, even, or neither. Okay, so I give you this. F of x is equal to x to the 5th plus 1. All right, there's a tendency to just be like, oh, look, even. Well, this is x squared. That's an even number, so it's an even function. Cubed, that's an odd number, so it's an odd function. 5, that's an odd number, so this function must be odd. Well, not necessarily. Let's look at this, okay? Let's plug in negative x and see what we get. Okay, so this becomes negative x to the 5th power plus 1. Well, what does that equal? That equals minus x to the 5th plus 1. All right, do you notice that this is not equal to, notice that f of x is equal to x to the 5th plus 1. Well, this is minus x to the 5th plus 1. So this is not equal to f of x. All right, so what we're seeing here is that f of negative x is not equal to f of x. That means it's not even. Well, what if I factor out a negative? This becomes x to the 5th minus 1. Do you know what this is not equal to? This is not equal to, okay, minus f of x. It's not, okay? This would have to be a plus in here, okay? Because, look, x to the 5th minus 1 is not x to the 5th plus 1. So what this means is it's not an odd function either. So this function is neither an odd or even function. Okay, it's neither. All right, let's talk now about what a piecewise defined function is. So a function that is defined by 2 or more, I'm going to stick with generally with 2 equations over a specified domain, is called a piecewise defined function. And so what this is going to look like is it's going to look like this. It's going to look like f of x is equal to, then you're going to get these brackets, and you're going to have equation 1, and equation 2, and then you're going to have domain 1 and domain 2. So what's going on here is we're saying, look, this function is defined by equation 1 over this specified domain, and it's defined by equation 2 over some different specified domain. And there's going to be no overlap between domain 1 and domain 2. And so what I want to show you how to do is, well, let me give you an example of just a very simple one here. We'll do this one first. F of x is equal to 3, and then when x is less than or equal to negative 1, or x minus 2 if x is greater than negative 1. Okay, so it's equal to 3 if x is less than or equal to negative 1, and then it's equal to x minus 2 if x is greater than negative 1. So look, what this means is if you want to evaluate this function, for example, if you wanted to find f of negative 2, you would say, okay, f is, the value I'm plugging in is -2. Well, that's less than -1, so I'm going to use this equation. So it's 3. If I wanted to find f of 4, well, 4 is greater than -1. Ha! So I would use this equation. So it would be 4 minus 2 is 2. So that's how you evaluate piecewise defined functions. So what I want to do now is I want to talk about how you find the graph, okay, of a piecewise defined function. Okay, so I want to sketch the graph. All right, so do you notice how there's two equations here? Okay, so you're going to need two tables of values. You're going to need for x is less than -1. Okay, so notice how I have this less than or equal to, so I'll start with -1, -2, -3, and I'm going to use f of x is equal to 3. Well, it doesn't matter. F of -1 is 3, f of -2 is 3, and f of -3 is 3. So I've got all these ordered pairs here. So -1, 3, -2, 3, -3, 3. So let me plot those, okay? -1, 3, -2, 3, and -3, 3. And this goes all the way up to -1 here. So what I'm going to do is, you can see here, it's just a horizontal line. All right, now here's what gets a little confusing. So this is for, now I'm going to have to sketch the graph of this, okay? And this is when x is greater than -1. So it seems weird, but you're still going to plug in -1, 0, 1, and I'll even do 2. And I'll show you what happens when you do this, okay? So you're going to plug in -1. So you're going to still plug it into this equation. So you get -1 minus 2 gets me -3. So my point here is -1 minus 3. But you notice how there's no equal sign under this? So what you're doing here, you're going to go to -1 minus 3, and you're going to put an open circle, okay? Because as soon as you get past -1, you're picking up with that value. So you really want to see, like, where is it going as I get close to -1, but we're not going to hit it. So you have a closed circle for the less than or equal to, and then an open circle for the strict greater than. And then just figure out the rest. F of 0 is -2. So 0 minus 2, I'm going to put a dot there. F of 1 is -1, because 1 minus 2 gets me -1. So 1 minus 1. And then finally, f of 2 is 2 minus 2, which is 0. So I have the point 2, 0. And you can see now here that this is just the straight line. So look, this is the part over here. This graph is the part f of x is equal to 3. And this is what it looks like until you get to -1. And then you're going to use x minus 2 after. So then this is the part that looks like x minus 2. All right, let's do another one so you can see. Let's graph the piecewise function defined by this. All right. Let's look at minus x plus 1 if x is greater, or excuse me, x is less than 0, and x squared if x is greater than or equal to 0. All right, so again, table of values. Okay, so I'm going to look here. I'm going to pick x, and then my f of x here is -x plus 1. And I'm going to get my ordered pairs. All right, so it's less than 0. So I'm still going to start with 0, and then I'm going to pick -1, -2, and -3. So f of 0, well, this is 0 plus 1 is 1, so 0 comma 1. But look, strict inequality. So I'm going to go to 0, 1, and I'm going to put an open circle. Now when I plug in negative 1, now be careful here. This is negative. Negative 1 is 1 plus 1 gets me 2. So I'm going to go to negative 1, 2. F of negative 2, well, that's negative. Negative 2 plus 1 gets me 3. And f of minus 3, negative negative is positive 3 plus 1 gets me 4. So negative 3 and then 4. And then you can see here it's a straight line, it's a linear function. So it's going to be here. So this is the part, and then open circle because it's strict inequality here. This is the part that looks like negative x plus 1. And then you can just pick the x squared, right? So now if an x is greater than or equal to 0, so I'm going to pick 0, 1, 2, and you can even do 3, but so 0 squared is 0. So you have the point 0, 0, but because you have the equal sign, you're going to put the closed circle there. Then f of 1, well, that's 1 squared is 1. And then f of 2, that's 2 squared is 4. And then we know this is a parabola from here. And then finally f of 3 is 9, which is off the chart here. So 3, 9 is somewhere up here. So you're just going to draw the parabola here. Like so. And this now is the part that looks like x squared. So look, the key here is to plot them separately. Okay, and then even though this is saying less than 0 here, still plug in 0, see what you get, and then just put the open circle for those strict inequalities. Okay, let's end now talking about the difference quotient of a function. So this expression, f of x plus h minus f of x, all divided by h, and this is when h is not equal to 0, is called the difference quotient of a function. Right? And you will see this. Okay? This comes up, this formula, this difference quotient, comes up in pre-calc and calc. Okay, so you'll get to see it again. So what I want to just show you in this lecture here is just really, really quickly how you find a difference quotient. All right, so let's evaluate and simplify a difference quotient. So find the difference quotient and just so we're clear, what is it? So it's f of x plus h minus f of x over h. 4, and let's just look at this one. Okay, let's look at f of x is equal to x squared plus 1. Okay, so the first thing you have to figure out, I see my f of x, so let's find out what f of x plus h is. So this would be, instead of x squared, it would be x plus h squared, and then don't forget you still have this plus 1. So you have to FOIL this out. Okay, this is where it gets a little, maybe not the best. So this becomes x squared, and this is x times h times x, so plus 2xh plus h squared, and then you have this plus 1. So now, your difference quotient now becomes f of x plus h minus f of x all over h. So let's just plug stuff back in. What is f of x plus h? Well, it's this expression here. Minus f of x. So what is f of x? Well, that's x squared plus 1 all over h. Now let's just simplify. So this is x squared plus xh plus h squared plus 1, and then distribute minus x squared minus 1 all over h. Check this out. What cancels? The 1's cancel. Minus x squared and x squared cancels. So this is 2xh plus h squared over h. Wow, check this out. Can you simplify here? Can you factor out an h? Absolutely. What cancels? HH. So this difference quotient is just 2x plus h here. So what we've done here is we have found this formula, this difference quotient, and then fully simplified it. Okay, so believe it or not, this is actually one of the easier ones. All right, let's now do a harder one. Okay, so this will be our last problem. So let's find and simplify the difference quotient for. Let's look at f of x is equal to minus 2x squared plus x plus 5. All right, so we need to find always this f of x plus h. So this is minus 2 times x plus h squared plus x. So now plus x plus h plus 5. Okay, what is x plus h squared? Well, we've already done that. Okay, we see that x plus h squared is x squared plus 2xh plus h squared. So this is minus 2 times x squared plus 2xh plus h squared plus x plus h plus 5. So let's distribute here. So this is minus 2x squared minus 4xh, I know it's a little crazy, minus 2h squared plus x plus h plus 5. Okay, so a lot going on here. So now the difference quotient is f of x plus h minus f of x over h. Well, I know this is crazy, so look. This is minus 2x squared minus 4xh minus 2h squared plus x plus h plus 5 minus, so f of x. So I have to subtract all of this. So I'm going to just distribute the negative. Okay, so it becomes minus 2x squared. So it becomes plus 2x squared minus x minus 5 all over h. Well, check this out. What cancels? X squared right there. Minus x. Wow, check that out. Minus 5 plus 5. Let's see what we're left with. We're left with minus 4xh minus 2h squared plus h all over h. Well, factor out an h here. Okay. So minus 4x minus 2h plus 1 all over h. Check it out. h's cancel. You're left with minus 4x minus 2h plus 1. And we got it. All right, class, I know there was a lot. There was definitely a lot to see here, but hopefully all these examples helped clarify these things. And, I say this every lecture, but, the more you practice, the easier this becomes.